Una pregunta para... Sí. ¿No tiene nada para comentar para empezar? ¿Sí? ¿Sí? Ah, perfecto.
Nada más que hacer aquí una maniobra. Tiene que reconocerlo primero. Vamos a probar. Avanzas, regresas y este de aquí.
Ah, con estos dos es lo mismo.
Ajá,
Ya.
y este es el...
Sí, ya.
No vayas a apretar ni este porque te reinicia la presentación.
Okay.
Sí, porque es el
Trataré.
control del PowerPoint.
Ya.
Nada más es este y los de arriba.
Los de arriba. De verdad, no confundimos.
Aquí ya está abierta, ¿eh? Cuidado. Sí. ¿Qué me lo llevo? ¿No te acomodaste con el otro?
Sí, que soy cantante, igual me va bien este.
Muy bien. No que sea de coloquio, Catherine, para que discutas de forma más...
Ah, bueno. Sí, porque ando con el tiempo de súper justo, así que...
Como tú prefieres. Usualmente la gente lo da en español, pero... sí.
Ah, me habían dicho al revés, me habían dicho que lo suelo hacer en inglés.
No, en español. Tenemos gente que no habla español, pero creo
Sí, no,
que
entonces,
ahorita
sí,
no sé.
solamente una persona que no habla español. Entonces,
Ajá, hay que darte en inglés, ajá. Pero no está por aquí, no lo veo por aquí. Pero como tú te sientes más feliz.
yo estoy en inglés, así que ya.
Sí, sí. Bueno, creo que ya podemos comenzar el coloquio del día de hoy. Bueno, hoy es un gusto tener a esta Lorena de la Universidad de Valparaíso. Ella es postdoc en la Universidad de Valparaíso. Y Lorena se graduó en el 2015 en Granada. Sus asesores fueron Pepe Mazagosa y esta Omaira, la de aquí del IRIA. Después se movió a Roma para hacer un postdoc en el IAPS y ahorita pues se encuentra haciendo un postdoc en la Universidad de Valparaíso. Así que, pues bueno, adelante por favor.
Good afternoon, everyone. I'm Lorena Hernández-García. I'm originally from Spain, from the Basque Country, but I'm now doing a postdoc in Valparaíso, in Chile. And the first thing I want to show you is this picture here, because one day I was walking in Valparaíso and I turned into the wall and I found this paint in there, which was quite amazing because it's exactly the type of galaxies I am studying. So I wanted you to see what type of city I live. It's a very artistic city. So today I will be speaking about reacting activity in the nuclei of giant radio galaxies. Here you can see a list of my collaborators, which are people from Spain, Italy, Mexico, Chile. So we know there exist a billion of galaxies in the universe, And what we think all of them have in common is the presence of a supermassive black hole in their centers. And some of them show nuclear activity in their centers, and they are called active galactic nuclei, and they present some peculiar characteristics. They show very, very high luminosities in the range between 10 to the 39 to 10 to the 48 erg per second. They also emit in the whole electromagnetic spectrum. And historically, they were discovered in the optical by having the presence of broad emission lines with full width maximums larger than 500 kilometers per second, superposed to narrow emission lines. Another property is also variability in the whole electromagnetic spectrum. And you probably heard that they are classified differently, or they are namely different, as quasars, Sieverts, radio galaxies, blazars. And I will come back to these classifications later, but for now, I just want you to have it in your mind. Let me explain you how we think a supermassive black hole or an AGN is. We can see it in this picture here. We have the supermassive black hole in the very center of the galaxy, and this is surrounded by an accretion disk, which is responsible for feeding the supermassive black hole. And this structure is surrounded by a distribution of different clouds. So very close to the supermassive black hole, we have what is called the Broadband Region, which is responsible for the broad lines in the optical spectra. And this is surrounded also by a dusty structure, which is usually simplified as a torus. And at larger distances, we have what is called the narrow line region, which is responsible for the narrow emission lines in the optical spectra. And about 10% of AGN, so relativistic jets. Why only 10%? It's still under debate. So it's something we need to study a little bit more. The thing is that depending on the wavelength we are observing, because we are astronomers, we usually observe at different frequencies, and we are focused more on one frequency. So I want to explain how we classify AGN depending on the wavelength we are observing. So as I said, historically they were discovered in the optical, and here they are classified as type 1 when there is the presence of a broad line, as you can see in these examples here, and as type 2 when only narrow lines are present in the spectra. Also, in the optical, we can use diagnostic diagrams to classify between H2 regions and AGN. These BPT diagrams are based on line ratios of different optical lines, and in the range of AGN, we can classify them as Sieverts, or we can differentiate between Sieverts and liners, which have different low and high levels of ionization. Then if we go in the radio, the usual way to classify them is as radio quiet or radio loud. This is done by comparing the radio and optical power. So when this ratio is larger than 10, they are classified as radio loud, and they're supposed to have a strong jet, while when this is smaller than 10, they are classified as radio quiet, and they are supposed to not having much radio emission. This was done historically, but now there are people who are saying that we should reclassify them as jetted or non-jetted AGN, but for historical reasons, I will just put this classification here. And if we go to X-rays, we can classify the sources as obscured or unobscured. This is done by measuring the column density in the X-ray spectra. And when this is larger than 10 to the 22, we call it obscured. And when it's smaller, we call it unobscured. So there are these different classifications, but the question is, if we observe the same galaxy at different wavelengths, do we have the same classification, or do we have different things that we are observing? So for that, we have what is called the unified model of AGN, which is supposed that depending on the view we have of the AGN, we can classify it as one or another type. So So here we have the torus that I explained you. So when we are observing directly through the torus, we don't have a direct view to the broadline region, and so we classify it as a type 2 in the optical and as obscured at X-rays. And if we have a direct view to the broadline region, we will see the broad lines in the optical, so we will classify it as a type 1 and at X-rays as an obscured. And depending on the presence or not of the jet, we will classify it as radio loud or radio quiet. So in principle, these different classifications match within this model. So if we observe through this, we have, for example, a Cipher2. If the luminosity of the nucleus is comparable to the one of the galaxy, we will have a liner if the luminosity is smaller from the AGN. And if we have a direct view, we will have a Cipher1 or a liner 1. And if we observe directly through the jet, we will have a blazar. Anyway, when this picture of the unified model was drawn, there was something that was not taken into account. And it's one of the things is AGN evolution, because we know that everything evolves, and so AGN also need to evolve. And there are people who have suggested that the accretion must finish at one point, and then something can happen in the galaxy that can trigger the nuclear activity and make the AGN to be active again. This can happen through merging of galaxies, for example. The problem we have to study this evolution of AGN are, of course, the time scales, and it's not the time scales of the galaxies, but the human time scales, because we don't live that much, so we cannot see the evolution of one galaxy in our lifetime. So it's this is a difficulty in studying this type of sources. But if we go in the literature, we can find some galaxies that allow us to study this evolution of AGN or these different phases of nuclear activity. And we have these giant radio galaxies, which are perfect laboratories to study this type of intermittent activity. And they are classified, well, they are defined by having linear sizes larger than 0.7 megaparsec. This is an example of a giant radio galaxy. This is Hercules A. And well, the linear size, I mean the size between here and here. And this is very useful, because the interesting thing here is that the time that it takes the matter to go from the nucleus or to the lobes can take as long as 10 to the 8 years. So if the nuclear activity has a smaller time for this phase, we can see the different nuclear activity in the same galaxy. And there are some examples in the literature that shows this type of nuclear activity. They are called double radio galaxies or X-shaped radio galaxies, and we can see their morphologies in the radio band are like this. For example, in double radio galaxies, we have all the structures which are from an old nuclear phase, and closer to the nucleus we can find new nuclear activity. And in the case of X-ray radio galaxies, we can see the old activity in one direction and new nuclear activity in a different direction. There exist different models to try to explain this radio morphology. So let me explain you these different models. One is the double AGN model, in which we have two different AGN, each one with its jet, and so we have this type of morphology. Another one is the backflow diversion model, is this one here. So we have the jet emitting in one direction, and because of the interaction with the medium, we have some matter going in a different direction, which would give place to this morphology also. Another one is precession from the jet, because we know jets precede. And the last one, and I think this is the one which is more accepted, is the jet reorientation, in which the jet emits in one direction, then the nuclear activity stops, and it starts in a different direction. well, this is great when we have this radio morphology and we can see different phases of nuclear activity. But what happens when the activity just started and we don't see this type of morphology? Are we missing a fraction of this type of restarting activity galaxies? So we are doing a work with some people in Rome and also here in Mexico and in Chile, and to try to understand this nuclear activity. And so for that, we're using a sample from Bassani and collaborators. They selected AGN in the hard X-ray band with integral and Swift, and they matched this catalog with radio catalogs with the MVSS first and SAMS, and found 64 galaxies. So an interesting result from this work was that 60% of their sample present sizes larger than 0.4 megaparsec, and 22% are classified as giant radio galaxies, which is quite impressive if we compare this number with the typical number obtained from the radio studies, which is about 5%. And very recently, Bruni and collaborators studied this subsample of giant radio galaxies and found that 61% of them saw the presence of a gigahertz spectrum, which means this is a plot from their work where you see this fit to the nuclei in the radio. And this type of sources are characterized by being very young. So they found an indication that within this sample, many of the sources have restarted activity in their nuclei. So the work I'm doing, and I started this long time before we got this result, is to do a multi-wavelength analysis of individual sources in this sample, in this subsample. And the work I will present you today is two galaxies. They are called PBC J2333.9-2343. This is a long name, so let me just call it PBC. And Markarian 1498. So the first one is this PBC. This cold laboratories, well, in principle, I was going to do this work when I arrived in Rome, because my PhD was about X-ray variability in liners and Seyferts. And for this galaxy, we thought it was something related with variability. So the interesting thing here is that it is classified differently when it's observed at different frequencies. So it is a giant radio galaxy from the sample in Bassani. In the optical, it is classified as a Seifert 2, so it means it has only narrow lines in the spectra. But at X-rays, it is classified as an obscure. So that would mean it is a type 1. Moreover, it is classified as a blazar at radio frequencies. So this means if we put these different classifications in the unified model, we're observing it from here, and from here. So there's something going on with this galaxy. And as I told you, we were thinking it was something related with variability, because the different classifications were obtained at different dates. So what we did was to obtain data at different frequencies and try to reclassify the source. We used data from Swift and XMM Newton at X-rays, from the VLA and VLVA at radio frequencies, and from the New Technology Telescope in Chile and San Pedro Martyr Telescope here in Mexico. And from this data, we have simultaneous data at X-rays, radio, and optical. So this way we could disentangle if this is related to variability or not. So now let me explain you what results we have from this study. These are the X-ray data. We obtained 2 different observations, both taken in 2015 and separated by about 6 months. XMM Newton also has an optical monitor that allows doing photometry in optical and UV frequencies. And so this is the photometric measurements. You see that there is no variability in this time scale. And here you can see the X-ray spectra. These are the 2 spectra, and these are the residuals from the model. there is a small variation, but it's very small. But the important thing here is the measurement of the column density. You see, it's around 10 to the 20. So we could classify it as an unobscured. In the optical, we used two different spectra. One taken in 2009 is this one. This is the one that was used to classify it as a Cipher-2. And we obtained a new one in 2015. And for the first time, we subtracted the galaxy contribution. So in blue, you can find the spectrum. In red, the model for the galaxy. And in black, the subtracted spectrum. So there is one thing here that between 2009 and 2015, we can see the presence of a broad line here. So attending to the classification of Osterbrock, we classified it as a Cipher 1.9, which is not very different from the Cipher 2 classification. And at radio frequencies, we had data from the VLVA. We obtained it in 2015 also at 3 different frequencies. And here you can see an image at 8 gigas. And what we see here is the presence of a jet, of a one-sided jet. We know it's the jet because it has a slope, a negative slope. And from this image, what we obtain directly is that the angle at which we are observing the jet has to be smaller than 40 degrees. And also we compared the luminosity, the flux of the nucleus of this part here with an old observation, and we found variability of about 300 millijanskis in about 11 years. And what you can see here is a spectral index map between the 8 and 15 gigas. And you can see here the presence of a nucleus. We know it's the nucleus because the spectral index is positive. So we are observing both the nucleus and the jet. And because we had this simultaneous data, we could do a fitting of the spectral energy distribution with this simultaneous data at radio, UV and optical, and X-rays. And here we needed to fit it with a Blazar template. And here we have 2 different models. In blue, we have the external compton, and in red, the self-synchrotron. And this gray part here is the Fermi detection after 1 and 5 years. And if you see, if it was self-synchrotron, we expect to detect it with Fermi, but we went in the Fermi archive and we didn't detect it. So this is why we say that external compton is preferred for this source. But anyway, independently of the model we used, the important thing is that the angle at which we are observing the nucleus has to be smaller than 6 degrees. So I've been telling you many different classifications. You probably didn't understand nothing. So let's put everything together from the different classifications. So we have that it is a Cipher 1.9 in the optical, which in the unified model would mean that we are observing like this, because we don't see a very broad component. It is unobscured at X-rays, and it is a Blazar from the spectral energy distribution. So we can handle with these different classifications if we classify it as a Blazar and we have a view like this. So we are observing very close to the jet, but not exactly through the jet. So we can see the broad line, and why the broad line is not that strong is something that we still need to work with. So great, we have a Blazar, but I told you that it was also a giant radio galaxy. So this is the image from the MVSS, from the VLA, and this linear size here is 1.1 megaparsec in the plane of the sky. So if we and the VLVA is just 1 pixel inside here, where we see the jet. So if we estimate this distance using an angle of 6 degrees, we obtain a size of 13 megaparsec, which is really enormous, because we went in the literature to find what are the typical sizes of this type of galaxies, and we found that the largest one has a size which is smaller than 5 megaparsec. And in fact, finding a galaxy which is larger than 2 megaparsecs was quite difficult, because there were only like 2 in this sample. So what we propose is that the nuclear activity was restarted some time ago, and the jet changed the direction, and now it's emitting in a different direction. I mean, the jet was emitting like in this direction, then something happened in the galaxy, and now it changed the direction and is emitting in this way. And here you can see a radio spectra. In red you can see the nuclear part, and in blue and in green you can see these 2 lobes. So you see here that while the nucleus is more or less constant, the lobes are decaying. So this means it's suggestive of aging of the lobes. So this is compatible with the picture of this restarting activity. This is a work that we published in 2017, and at that time I found that the optical spectra were so interesting that we obtained new optical spectra.
Lorena, a question. Perhaps this is a dumb question, but how do you know that those lobes are from the galaxy? I mean, if you come back to the figure, I see that there are also 2 sources.
Yeah, we searched for this, and these are other galaxies. These are other things, but this is part of the galaxy.
Yeah. So my question is, how do you imply that this comes from the galaxy? Do you need to observe an optical or different bands, or
to know that this is part of this galaxy?
That those are the jets from the galaxy.
Well, we made a very deep image with the GMRT, and you can see that this is part of this. The emission is going in this way, and also in this way. And these are not galaxies; these are lobes. So they need to be from this galaxy.
From the contours, you can see.
Yeah, there are contours that are going in this direction here.
What's the environment of the galaxy?
It's an elliptical galaxy, an old galaxy. No, it has no neighbors, because we were thinking we take a look to the environment, and if we find any other galaxies. I found that there was galaxy very close, but the redshift is different, so it's not a neighbor, because we were because if this is restarted nuclear activity, we were thinking it was something related with a merger, but we didn't find any indication of that. It's just an isolated galaxy, it's not in a cluster or anything. Okay, so as I was saying, I found that the optical spectra seemed interesting, so we decided to take another one in 2016. So these 2 here, well, this is the H beta and oxygen 3, and this is the H alpha region. These 2 are the spectra that I already presented, and these are new spectra. These 3 are taken from San Pedro Martyr, and this is taken from Chile. So this spectrum and this spectrum were obtained about with 1 week of difference. So there are a couple of interesting things here. The first one is the variation of the broad lines. You can see that from here. Well, here, let me explain you the different components. This is a fitting of the optical spectra. In green, we have the narrow line region. In yellow, we have the broad line region. And we needed to add another component, which is compatible with being an outflow. And in red, there is the total model. So the first interesting thing here is the variability of the broad lines. You can see a big change from here to here, and also from here to here. And also, we didn't see any broad line in 2009 and 2015, but we see a broad line in 2016. And also this broad component that we needed to fit, that we think it's related with an outflow. And I think, and correct me if I'm wrong, that this is the first time that we found an outflow in a blazar. We had also observations from the SWIFT satellite. It has also an optical monitor, so we can do photometry, well, a light curve at X-rays. This is in the X-rays, the yellow one. These ones here are from the optical monitor, and I forgot to put here another one from the 8 alpha, from the broad 8 alpha, which goes also in this direction. So this is more or less constant, but at the time we took the optical spectrum, we see a change in here. This is a variation of about 60%, and also we see the same behavior in the broad 8 alpha line. And so for this, we suggested that the jet is at least responsible, at least a little bit, for the photoionization of the broadline region. And this is another paper we published last year, and we still need to work a little bit more on this galaxy because it is very interesting. And so we have different data. We asked for a monitoring at radio, optical, and X-rays, and I hope this will be published soon. Yeah. Here, yeah. I cannot be confident on that change. We see there might be a little change, but I cannot confirm from this spectra because you see the components are not so broad. But I hope with this monitoring that we already have, I still need to analyze that data. But I hope from that we can see if the outflow is changing or not. But from here I cannot confirm. The width? It's about 2,000 kilometers per second. It's quite huge. It's a little bit shifted. Not that much, but it could also be, well, I mean, it is an outflow, but it could be a different region from the narrow-line region, for example. Exactly. Exactly, that's the thing. Exactly. Yeah. Yeah, exactly. That's what we think is an outflow, but with the data we have, we cannot say many things. I hope we have new VLT data, so I hope from there we can study it a little bit more in detail. Okay, so now let me introduce you the other galaxy we've been studying from the sample in Bassani and collaborators. This is also a giant radio galaxy. It has a size of 1.2 megaparsec. This here is a Hubble image from the galaxy, from the very center. This is an oxygen 3 line, and in red you have the 8 alpha. And this is the direction of the jet, of the long scale jet. So this is from the sample of Bassani. This is why it called our attention, because these structures are misaligned by about 70 degrees, and this is quite unusual, because usually when at these small scales, if the jet is aligned with the narrow line region, which is supposed to be the oxygen 3 emission. So we went in the literature and find what people said about this galaxy, and there's work from Kiel and collaborators who suggested that this is a faded AGN. So this means that the AGN is no more active, but this emission here is from the past nuclear activity. But another work from Eguchi and collaborators at X-rays fitted the data with a very obscure AGN. So it can either be a faded or an obscured AGN. So we were curious about this, and we obtained data at different frequencies from the archives. So to do this work, we use Spitzer and mid-infrared frequencies at X-rays with Chandra, Swift, XMM Newton, and NuStar, with the VLA and VLVA at the radio frequencies. We also obtain a spectrum from the San Pedro Martyr telescope, and we use the data published by Kiel with the Hubble Space Telescope. So I will show you what are the different things we observe at different frequencies. This is in the radio. This is data from the VLA. The sizing here is 1.2 megaparsec, and this is the image from the VLVA. So it is just 1 pixel inside of here, like in PBC. And this spectrum, this radio spectrum here, is from the work of Bruni that I spoke about before. This means that this part here is very young, but these lobes are suggestive of a very old galaxy. So this already suggests restarting activity of the galaxy. Then at mid-infrared frequencies, these are the spectra with the Spitzer. Well, it's the same, but we fitted it with 2 different models. We needed to fit it with a torus model. So this is a smooth distribution, and this is a clumpy. The interesting thing here is that both models give a very similar result, and the important thing is that with this fit, we can obtain the parameters of the torus, and in particular the angles at what we are observing. So we can obtain, with this, the opening angle of the torus. This means you information about the width of the torus, and also the inclination to the observer. So in this galaxy, we have something like this. We have a small torus, a thin torus, and we're observing it a little bit from above. But anyway, it's interesting that we needed to fit it with a torus model. So this means that there is something active. Then in the optical, this is the spectrum we obtained from the San Pedro Martyr. We subtracted the galaxy. So in black, you have the original spectrum. The models are here, and this is the subtracted spectrum. So in this case, this is a Seyfert 1.9. It has a broad component here. This is the fit of the optical spectrum. We also needed to add a component which might be an outflow also. And also an interesting thing here is related to the star formation history of the galaxy that we could measure with starlight. And this suggests that at about 10 to the 6 years ago, there was an explosion of star formation. We need to be cautious with this type of information, because it depends a lot on the models, but it's compatible with the other things we are observing. And then at X-rays, we have, this is the Chandra image. This is in the soft band between 0.5 and 2 keV, and this is in the 2 to 10 keV. So here we see, for the first time, this data, we are publishing this for the first time, and we see extended emission here, which is very nice. And here we have the different spectra of different instruments. And before putting all together, we did a variability analysis of the source, because we know this type of sources are very variable. But in this case, we found that there were no variations in about 11 years. So we put all the spectra together to do a fit of the spectrum. And for this, we used a model called Borus, which represents a torus, and we used the parameters obtained from the mid-infrared, the angles, so we can obtain the more information we can. So we found that the column density is very high, of the order of 10 to the 23, which suggests that this is a highly obscure source, and it is indeed very powerful. It has a luminosity of 10 to the 44, which is not that usual in this type of sources. So the first important thing about this galaxy was to check whether it was a faded or an obscured AGN. So with the data we have, we found that in the VLVA and in Chandra, it shows a point-like source at these frequencies. So this is indicative of something active. And also from the mid-infrared data, we needed to feed it with it is dominated by the torus emission. So this means that there is an AGN in there. What we did to confirm that we have an obscured AGN and not a faded AGN is to compare the ionization luminosity given by Kiel, which is of the order of 10 to the 43, and we compared it with the volumetric luminosity in the nucleus, which we obtained from the X-rays, and this is of the order of 10 to the 45. So this means that the nuclear region can be photoionized by the AGN. And what we found also is that the column density is very high, in the order of 10 to the 23, and so this confirms the presence of an obscured AGN, which is not faded. And as I told you, this also suggests that the nuclear activity was restarted, basically because from Bruni and collaborators we found that it has a GPS source in its center, and this means that the age has to be in between 10 to the 2 and 10 to the 5 years, and this is in contradiction with the age of the lobes, which can be as old as 10 to the 8. So it's not possible that the nucleus is feeding the lobes, and this is compatible with restarting activity because this reactivation of the nucleus happens in about 10 to the 4, 10 to the 8 years. So as I was telling you in the beginning, I think this type of galaxies are related with this type of galaxies in this particular case, because we see the old lobes, but we don't see the new lobes. But this is probably because it is in a very early phase of the reactivation of the nucleus, and so we cannot see the new nuclear activity in the radio band. So probably, yes, we are missing a fraction of this type of sources. But there's still something interesting in this galaxy, and is the extended emission we observe from the HST. This is a combination between oxygen 3 in HST, this here, in red it's H-alpha, again from the HST, and the blue is the soft emission in Chandra. And so you can see that, and in yellow there is the direction of the jets. So for me, at this moment, I think that there are two different structures here. One is this part here, which Kiel and collaborators used Gemini MOS data. This is the IFU data, and so they could estimate the velocity, and they found that the rotation of this part here is the same as the rotation of the galaxy. So this part is probably related to photoionization of the AGN. It's also in the same direction of the jet, so this is compatible with the general picture we have of AGN. But there is this emission here at larger distances. This is to about 7 kiloparsec, and I think that this is something related with a different thing, because we did a simulation to try to check if the nuclear part here is able to photoionize these large distances, and we found that it's not. So this should be related with a different process. Here we have the spectra of the nucleus. The black is the nucleus, this part here, and the blue one is this one here. So we found that if we put this in BPT diagrams, it might be related to H2 regions. So this might be something related with star formation. And also Kiel and collaborators, they used the HST image. They put a model, and they found that they found some residuals, and so they proposed that this is something related with a merger. So if this is a star formation, it could be related with a merging event that happened some time ago, and this is something related with that. But from the data we have, we cannot say anything. So I hope we will have new data soon to try to understand what is happening in here that gives place to this morphology. It could also be related with an outflow, but we don't know, because we see there is a presence of an outflow in the nucleus, but because we don't have no more data in here, we cannot differentiate between a merger or an outflow. So I hope I can say something about this in the near future. So just to summarize, I want to tell you a couple of things. The first one is that multi-wavelength analysis of AGN is very useful in understanding this type of sources, because it gives us many different information of different things we're observing in the nucleus. So putting all together gives us a more general picture of AGN. Also from the work of Bassani, X-rays might allow to select sources that are undergoing a restarting activity scenario, basically because X-rays allows the detection of powerful sources, of active sources. And also, as I told you during the talk, we are probably missing a fraction of restarted activity sources, because we are usually searching for them in the radio band, and until we don't see these different emissions, we cannot say that they are passing through a restarted activity. And for now, we have studied two different sources. One is PBC, which is a galaxy that was a radio galaxy, and something happened, and then the direction of the jet changed, and now is emitting in a different direction through a restarting activity episode. And in here, the jet seems to be responsible, at least in part, for the photoionization of the Broadband Region. And the other source is Markarian 1498, which is also a restarted activity, because we see that it has a GPS in its center, but it has these all lobes, so it needs to have gone through a restarting activity scenario. And we can confirm that this is an obscure source and not a faded AGN, but we still need to know what is going on with this extended emission I explained to you. So this is all. Thank you very much for your attention.
No. Questions?
In the Chandra image that you showed of the second source, yeah, there are traces of the jet there in both, in the... No, because the jet is in this direction. Okay, so it's perpendicular to the jet, what you see in the Chandra image.
Yeah,
those little extensions.
Look, this is the blue, is that Chandra emission, and so there is something here. I'm not sure. I didn't say anything about this because I'm not sure this is true. Okay. But the jet is in this direction, so it's not related. I mean, you see this. There is some elongation here, and it's in the same direction of the jet. So I think it is related with the jet emission, but not this one.
Okay, but it could be another outflow. That's what you are suggesting?
Yeah, it could be an outflow, but we don't have data to check that. But the spectrum of one of these parts it seems to be related with an H2 region, so might be something related with the star formation. And this is where we are suggesting that it may be something related with an aftermath of a merging event.
Have you attempted to model like this Chandra emission that you have, like an extended component and
we tried to obtain a spectrum from Chandra, but it didn't have so many counts. So yeah, we could try to do that. No, that might be interesting. But we have we have an approved observation with Megara of these emissions here. So I hope we will be able to understand a little bit more when we have this data. But for now, we cannot say anything.
I had another question. You mentioned that you had BLBI data. None of these sources has double nuclei?
No, no.
More questions?
What could be the condition or the mean condition for restarting an AGN?
Well, this is a good question. One could be just that you have accretion, and then at one point the accretion finishes, and then something can happen like a merging of galaxies or secular processes that could reactivate the nucleus. Those are the possibilities.
What do you mean with secular process?
Secular processes are something happening in the galaxy. Like, for example, if a star goes around the supermassive black hole, it can change something.
Thank you.
More questions? I have one. So I know that you said that when you did the analysis with the starlight and trying to infer the star formation history of the galaxies, we should take care with that results. Yeah. But did you assume some parametric form of the star formation history, or is just non-parametric star formation history of the galaxy, and you?
No, yeah, this is parametric unit. This is why I'm saying that you need to have some caution with you when explaining these results, because it depends on many parameters that you need to assume. So in this case, because it is related with our interpretation, but in principle you need you cannot confirm that, because it's something you cannot say this happened 10 to the 6 years ago. It's quite difficult to say that explicitly.
So you assume a parametric star formation history for?
Yeah.
What did you assume?
I can give you the details later if you want. I don't remember all of them. It's a huge model.
Okay. Yeah. No worries. More questions or comments? If not, let's thank again Lorena.
Thank you.
And we have After Paris.
Pero sí hay, ¿verdad? Sí. Magnetismo, digamos, con campos magnéticos. Sí, de hecho ahora hay que poner una